Michela is an associate professor at the chair of design informatics and the head of digital technologies at the Department of Architectural Engineering and Technology at Delft University of Technology, where she also leads the research at Lama Laboratory of Additive Manufacturing. Her work focuses on computational design at the intersection of architectural design and building technology. It puts forward computational design to integrate engineering aspects into the architectural design conception towards architectural design innovation with a sound fulfillment of performance criteria. She developed methods of form generation, performance assessment, design exploration, and optimization by means of new computational methods, integrating multidisciplinary perspective. Additive manufacturing is key in her research, and today she will be presenting integrated performance by additive manufacturing.
Thank you very much. And as Manya kindly introduced, yes, exactly. What I will be presenting today regards the integration of different performances by means of additive manufacturers, interpreting additive manufacturing as an opportunity to explore performative aspects of the design. And what I mean with performative aspects, well, I always like to start with the idea that architecture is quite of a complex system that integrates a very large variety of different performances. So what we actually expect from architectural design is a fulfillment of this broad range. If we think of the role of building components, I like to think of them as kind of the grammar that allow us to compose this overarching and overall system of complexity. And that is actually the perspective that I will be taking today. So as Manya introduced, the larger picture of the research I'm dealing with is indeed on the broader spectrum of computational design. And I like to place it at the intersection of architectural design and building technology, exactly because the idea to me is the integration of engineering aspects, usually delegated toward the end of the process, much more at the very early stage, really in the conceptual phase of the form finding, therefore. One way to do this, I think most of us are familiar with such a loops in computational processes, where I always like to look at this process as an iterative workflow that revises multiple times the form, the shape, the geometry, and uses the geometry in order to integrate inputs that we have in terms of performance assessments, where performances are seen in an interdisciplinary way of inputs, and therefore the complexity of these and how advanced algorithms, we look at search algorithms, but more and more at machine learning approaches as well in general, can help the exploration of this variety. And to me, that is where actually materialization really links in, where I absolutely don't want to delegate this at the end of the process, but I rather advocate the need of integrating not only the constraints, but really taking advantage of the potentials that new materialization methods allow us to consider and to integrate in the form finding. Now, in this respect, additive manufacturing to me plays a big role for multiple reasons. The higher freedom in terms of geometry is obviously one clear reason, but I'm also, to join into previous discussion as well, I'm also very much fan of integrated functionalities, where indeed the geometry can be used to bring together within one component different performances and thereby different functions. What I will be doing in this short presentation, I will just briefly touch upon a number of different projects. I'll therefore be perhaps a bit shallow on that, but I prefer to give kind of a broader overview to yeah, to convey indeed like the breadth of the different performances, and each of them, of course, we develop in collaboration with experts from that field. Several of the projects you're going to see are actually developed at LAMA or together with LAMA, the laboratory of additive manufacturing at our faculty. The first project I'm introducing is a reinterpretation of a trompe wall. Now, if we think of what trompe walls usually are, we always think of elements that are quite massive, obviously, with very high weight, but also obstructive. They are usually like big block of concrete placed in front of our windows or glass facades, with the idea of buffering peaks in temperatures. Now, this project reinterprets them in the sense that we were trying to achieve the same thermal effect or a better thermal effect, but by using lightweight materials or more lightweight materials and translucency. Now, as such, we've been working with advanced materials such as phase change materials together with layers of insulation. We looked into aerogel as again, like extremely lightweight and translucent type of insulation. And we collaborated with colleagues at building physics in order to kind of enhance the thermal behavior of those materials by means of the way in which they were distributed and encapsulated. And this is where additive manufacturing kicks in. We looked at how to shape kind of the skin of it, the container of it, in a way that this can be shaped in order to enhance the needed airflow, the needed solar radiation, and other aspects that were somehow crucial and vital in order to obtain the intended cycle in the thermal effect of the materials. Now, you just see actually one concept of this. In reality, this method is was applied and studied on a set of different concepts, but I picked this one as a full kind of demonstrator of the idea, where the full workflow was then somehow also integrating structural aspects and consideration that regarding the printability of the item. You see some of the studies that were initially made in order to calibrate and the printing temperature, the speed of the temperature, the layer thickness, in order to, again, combine a certain speed of the process versus still a certain precision, or at least the amount of precision that we needed in order to create both the joints and the channels and the streams internal to the overall shape when the different materials were being encapsulated. You see the prototyping part of one panel out of a modular system was envisioned for a facade, and a close-up look into some of the details till the full-scale installation of one module for monitoring, for thermal monitoring at the Green Village. This is the team that was working on the project. The core team, obviously, others were also involved, where Stavroula and Tudor especially were the ones that really worked hands-on and invested a lot in the printing part. Now, a similar approach, but on a completely different type of performance, in this case, not thermal, but acoustic, was the subject of ADAM. In this case, we again had kind of a parametric grammar. The grammar we were using here was based on the tubes, which had a variety of length, diameters, and the number of tubes that they were therefore giving a certain porosity to the surface where they were integrated. And we kind of use these in order to tune acoustic performances. I'm going to show part of a video. And here I must apologize, I forgot to share the audio when I was sharing the screen. So I will unshare for a moment the screen and reconnect immediately by sharing the audio. Yeah, here we go. Now it should work. And I'm gonna do it only for, due to time, a small part of the video.
Frequencies of noise nuisance.
In this project, we developed a digital.
Does it work?
Digital workflow where designers, architects, engineers can actually craft acoustics and develop components that are optimized for acoustic performance.
The resulting design are then produced by means of additive manufacturing. We use additive manufacturing because of its potential to produce a large variety of complex shapes. It gives a lot of freedom in the complexity of the geometry, but also it allows producing pieces which are unique, meaning not necessarily based on industrial repetition.
The acoustic principle we are using is based on quarter wavelength tubes, and they absorb sound via so-called viscothermal damping. Inside the tube, a standing wave emerges, and that standing wave determines the frequency where sound absorption appears. The length of the tube and the radius of the tube both determine that specific frequency. Well, we can also achieve broadband sound absorption by including different kinds of tubes, so with different length and radius, in one product.
The computational optimization required a mathematical model. For this model, we used formulas from literature, which were anyhow not enough. Those formulas contain a specific absorption coefficient, which we derived and validated for a large set of measurements. Those were specifically fine-tuned for the case of 3D printing, which wasn't explored before.
Simulations, of course, are not enough, so we also had to do a lot of measurements. Typically, measurements are done in a reverberation room.
It's a huge room full of reflections, and by measuring in this room our sound absorbers, we are able to calculate their acoustic performance. The results are really promising, especially when it comes to lower frequencies. And we are really hoping that we will be able very soon to launch a ready product that can enter the construction industry.
I stop here for a matter of time, and there was the link on top in case you want to watch the full video. But the message of that, coming back to the process, we kind of can optimize the number of parametric elements I was mentioning about, the number of tubes, their length, the diameter, and automatically, with a tool we developed, lay them down into distributions in principle any shape. You see the example of an hexagon, but could be in principle any geometry that a designer can therefore input, with the effect of then being able to absorb targeted frequencies, being that either in a very limited spectrum that is the target in a certain project, or vice versa, trying to broaden up the number of frequencies to achieve broadband absorption. We had also a number of students, master students, collaborating and somehow joining into the project occasionally, with their, especially with their thesis. It is one example of those by Sebastian Costa, where in this case, different simulations and different small prototyping, and again measurements. In this case, with the you see an example with the impedance tube, were somehow linked again always to this idea of how to bring this into geometric configuration that would lead to new designs and new way of thinking the integration of the performance into the design. And again, you see the team that was involved in the project. Again, moving to different type of performance, in this case, daylight. This was a project developed in collaboration with Practice. It was for a shading system, which is not realized, I need to say. Now, the target was this large glass facade. They needed kind of a customized shading in order to achieve intended levels of daylight in the big open space that was on the back of the facade in the indoor area, where the requirement there was kind of subdivided per different zones. I don't go into the details of the optimization part, but an optimization or a set of iterative optimization developed together with the architects were actually performed and led to a rather large variety of different panels throughout the entire facade, for which then additive manufacturing was taken into account for the production. In the additive manufacturing part, we have been exploring different options for the manufacturing, closely related to alternatives in the parametric geometry. You see a preliminary study in case of rather thicker elements with a certain amount of infill that was then gradually more and more reduced into a kind of one-layer approach that was saving a lot of material as well as being extremely faster in the production, which resulted more or less in a total of 9 hours time per each panel, which is still a relevant amount of time. I was somehow considered to be acceptable for the entire production. The entire production would have been of slightly more than 700 panels, each of which was on a weight that was approximately around 8 kilos. You see again the team that was involved. I want to come more or less to a conclusion. I still show a couple of shorter examples that are kind of more conceptual. This was a project that started as a master thesis and then developed into a short research project, and is a concept for a facade system. But it's still, so it's really intended as an exploratory direction, but I think it still has a very high value in terms of this idea of integration of different performances, where in this case, the inner core of the element is delegated for thermal resistance, and different geometric configuration were actually studied in order to enhance as much as possible the thermal resistance, combined with an outer element produced at one go for channeling liquids for thermal storage, and actually as a movable thermal storage able to bring and accumulate it on one side and moving it to the other side. Now, again, the entire project was meant to investigate the level of different performances that could be integrated in each panel. I don't show the entire set, but it is to give an example of different options for the inner core, where this idea of cells were investigated in different geometry to measure via heat flows measurements, the thermal conductivity of each of them. And at the same time, they were kind of designed and developed in order once more to try to speed up as much as possible the production, where, for example, we were trying to exclude sharp corners and rather having a smooth path for the printability of the object. You see some quick prototypes that were being made, but then again, printing time was in this case required a relevant amount of hours. Master theses that were connected to in this project as well. You see the example of the graduation project of Valeria Piccioni, in this case with the goal of trying to integrate additional performances, so not only thermal aspects that were being also in this case explored via simulation as well as measurements on samples, but also structural performance, which was integrated in the optimization of for the form finding. In a very last note, I just want to open up on a project that is more on a set of, let's say, investigations that are rather actual, still ongoing. Those are being developed in collaboration with the team of Christian Lauter. They are specialists in glass, and in this case, the topic is the combination with thin glass. So something which is extremely flexible, very transparent, and yet has great mechanical properties. And the idea is to combine inner core, which are 3D printed, kind of obtaining sandwich panels that give in different configuration structural stiffness to the elements, but then eventually also other properties. We're combining also some option for partial sun shading, where the ideas of those master theses was really the investigation also of the properties of the material, including not only the mechanical resistance, but also, for example, the UV resistance, what you see here on the left, or the fire resistance and the time that actually is required for the time the material takes to melt. And so on and so forth, which I think, and I want to conclude with this message, is still something which is a very important part of the exploration when we work with additive manufacturing for the built environment. The understanding of the behavior of the material, and then the integration, including in normatives and codes that we need to respect, is something which I think is an important milestone that needs to be further researched. Now, even though with, let's say, only quickly touching upon each of them, but I hope that the different projects were kind of able to convey this idea of integrating different performances and how the materialization and in this case, the additive manufacturing part can open opportunities that are still I think for us to take advantage of in this broader loop of performance integration. And I'm very happy to answer questions or participate to the debate, of course.
Well, thank you, Michela. Quite diverse set of projects. I just wanted to ask one question in terms of collaboration with the engineers. You seem to have a lot of collaboration going on, and how does that work in terms of, is it like generative process where they actually help with developing design tools that already inform the performances while you design, or it is post analysis after the design is applied and then refinement of design and then back and forth? So yeah.
Yeah, thanks. It's a quite relevant question. No, it's not afterwards. Absolutely not. We try to really have it as a very early input. Nevertheless, in most of the cases, the computational tools are developed by our team. So, well, depending obviously with what team of engineers we collaborate. There was an example where Arup was involved, and then in that case, they also directly contributed, for example, to the development of the script that we were using. But let's say, generally speaking, the most common case would be that and the different engineers, I take, for example, the teams of building physics, studies. So let's say, help us extracting, or they extract themselves the principles where there are direct influences of geometry in the performance that is each time being investigated, and what those principles are. And then that is a matter of capturing those principles and encoding them into a computational workflow that then allows the generation of the form. And that is definitely an iterative exchange that is really done from the very early stage in collaboration with the engine. So no, it's absolutely not post engineering, or at least that's what we try really to kind of not promote.
Yeah. Oliver, you were going to say something before I
No, go on. I have a question, but you have another one, so go ahead, please.
Yeah, it was a very quick one. I was wondering if you mentioned at some point aerogel, and I was wondering if you guys have also explored PCM as any material in the building envelope, or it was mostly aerogel.
No. Yeah, it was also PCM. So the way in which that specific project was working is that we were combining indeed the phase change materials in internal streams and channels that well, it was kind of delegated to capture the heat, and then we were using obviously the heat, the latent heat to enhance the process. But now the aerogel is because we wanted that effect to be a kind of extreme on one side, the side that would be, for example, exposed to solar radiation, or the side that would then turn to release the solar radiation. And we wanted that effect to be minimized on the other side. So we kind of placed one layer of aerogel in a specific, well, it was encapsulated in, let's say, one cavity. There was therefore on the one phase, that's why it's called double phase. And one phase we were minimizing the thermal resistance and trying to enhance as much as possible this heat exchange. And on the other side of the element that is turning, we were actually increasing as much as we could the thermal resistance, and there where aerogel was indeed being encapsulated in the system.
Thank you.
Thank you for the presentation. You mentioned already that you of course explore and experiment about the material performance on the long run. You expose PET to UV radiation, but you didn't talk about your findings. Do you have one? Like, I could very well imagine the material being used in the interior or as a shading device between glass panels. Would they actually work on the outside of a facade, as you've shown the one design proposal with this differentiated shading system?
The shading system was in PVDF. No, we did exclude indeed. At the moment, in our experience, we didn't find a proper way in which already PVDF was at the limit of meeting the requirements. And now we didn't like back then, and this was a project a few years ago. So I think that by now there are actually better alternatives. PVDF is rather even toxic when you extrude that. So it's not like a direction that we were really promoting as fully optimal. But in terms of meeting certain regulations, the weather resistance, the UV resistance, the fire properties, and so on was definitely one option that was working much better than PET-G. The other project, the one that you were seeing in with the test I was showing here, we did test on a set of different thermoplastics, but the one you were seeing here was the PET-G. That the resistance is rather limited, and then indeed it's a matter of understanding, or at least the project there was about how limits can be integrated within, in that case was a sandwich panel, so it should still, for example, in case of fire, trap the material inside. So, and the element is not a main load bearing structure. So again, I think in that case was a matter of understanding what the limits of the material are and designing accordingly. But no, we would not delegate entirely the both fire resistance and UV resistance were, I don't remember the numbers on the top of my fingers, but were in any case too low to meet standards for the outdoor. Or for unprotected, in case of fire, for unprotected elements that would, for example, be able to melt directly down and therefore hinder users, for example.